Hello everyone, in this lesson we're about to cover how can we estimate water analysis. That is one of the most important parameters for estimate water saturation, and also RW, formation water resistivity. So we are going to play three techniques of this. Ionic water analysis, that we are going to use some water sample for that ionic water data. RW from water bodies and pockets that only require logs information, and the classical one may be estimate water saturation using core water saturation until you achieve a match with water saturation. So this is the article to teach us how to do that, and that's the web page on our geologic.com website. So these are the screen, this is the main screen, and this is some of the theory, total dissolved solids and the ions, the cations and anions, and to weight them properly, and some comments on how reliable has to be your water sample. So your water sample have to have chemical reliability, have to have good quality lab tests, has to have space representativity and time representativity. So it should be taken at the initial of the reservoir exploitation. So have a look on these comments and let's start right away. This is an example of a water analysis that was measured in the year 1973, and think. In the US we have a lot of public data you can access from the state's websites. So this is very old, decades ago, but you can study your well, you can study your reservoir. So here we have the water analysis cation measurements in parts per million or milligrams per liter. That is quite similar. Like sodium, potassium, lithium, calcium, and magnesium. In some cases they measure iron. Negative anions like sulfate, chloride, carbonate, bicarbonate, hydroxide, and hydrogen sulfide. Take this measurement and let's compute salinity. Basically, you will see that will be quite similar to the results. But here is something that is suspicious, that the total cations count, milliequivalents per liter, it is exactly the same at the second decimal to the total anions. Somehow, perhaps they complete the information to match. You see the chloride value, this is too round. So let's take this. What you have to do is to take these values and load those values into the water analysis module. So you have to enter each value of the readings, the parts per million, which is approximately the same as milligrams per liter. Your oil knows the balances of your molecule and the molecular weight, grams per mole, and it computes all the equation inside. You hit, for instance, clear results, calculate, and this is it. You have a total charge of positive cations, 1500 something, and a total charge of negative anions, which is 1600 something. When you touch water, you expect the water to be neutral. You don't expect to touch the water and have an electrical discharge. The balance, the cation minus anion difference, should be usually between 15% or less to be acceptable. In this particular case, it is very good. 2% of difference is very good. The equivalent salinity, sodium chloride salinity, is 90,000. In most of the cases, this is quite similar to TDS or total dissolved solids. This formation water is very salty. That happens many times in Montana, in the states of Montana and Wyoming. This is quite typical. Now let's try to estimate water salinity from core measurements of water saturation. So we have a nice example here. We have here a track with water saturation. We have the red dots with the measurement of water saturation measured in the core. Likewise, we have the estimation of final irreducible water saturation. This is this curve here. And we have our final estimate of water saturation from logs. So here you see, in this particular region, you see that there is a nice match. Core water saturation points and also this here. So you see the difference here between the water saturation and the irreducible saturation is this zone that you see here. That is a zone with free water. That is a zone that you expect to produce water if you take a perforation there and put the well on the production. There is another formation here, which is Phosphorya, and the next one was 10 slip with 5 different members inside the formation 10 slip. So we have water saturation in Phosphorya that matches more or less well the curve that we estimated. Now the salinities from Phosphorya and 10 slip are completely different. So let's see how can we take care of that. what we're going to do is to move the salinity from one package and the other, from one zone and the other, and see how the match is good or bad. So let's start with this example to the left. Here in this example, check the equation. To the right is the example window log. So open this one. It has a lot of functions. It was 39. Let's open this one, merge salinity. So this is a compound salinity model. We have a salinity for phosphoria, 13,000, and we have a salinity for 10 slip, which is around 3,500. Okay, this is more or less the expected value. Here in this example, we're testing a case. We put too high salinity. What happens? You open here, merge salinity. Let's compare. So instead of the right value for 10 slip, which is around 3,500, we're going to set as an example to match or this match. We're going to put 7,000 and see what are the results, how expected. You calculate that. You are calculating this curve. You are calculating an output salinity, this curve. But many other computations depends on that salinity. So you have to update your full model. So you go to function workflow, all the equations, toggle off, toggle on. When you click run all check functions in sequence, you update all your model. Let's do that. Let's click on here. Okay, let's see the results. Go to display and see how it behaves. This is a case where we put too much salinity. And let's compare with the display with the right one. Go more or less to the same depth. It's more or less this one. Not only you see a completely mismatch between the water saturation core points, they're shifted to the right, or the water saturation curve, which is shifted to the left. We don't have a match. It's a mismatch. So you here in the right window, we have a difference between the water saturation and the irreducible water saturation in black. So that difference between the water saturation SW final and the black curve SW irreducible is free water that is supposed to be produced if you open the well here for production, you perforate the well or whatever. So we have some water saturation, and here we don't have any free water saturation. So if you put a higher salinity, you are going to expect that your model won't produce enough water. You need to do a simulation work, a forecast. You will find that your model is too short on water production. You move the salinity, compute all your workflow one by one. You simply do a single click and your oil change. All the equations one after one, they are recursive and they find the dependencies. You specify that and you display. That's automatic. Let's compare now what happens when we use a too fresh salinity. Open this case, this log, and see what happens. Flow, let's see what we put in salinity, merge salinity. The salinity for 10 slip. Well, this is some sort of extreme case. This is a water that is too fresh. So this is an extreme case, so it's a very fresh water. Let's see how it runs. So we have salinity for 10 slip, 1,100, 1,100, compared with 3,500. Let's see how it behaves. You run that, and you put your workflow, your function workflow. Make the display and compare. This is the original display. Let's see what happens. We put too fresh water, more or less the same sum. Okay, you put a fresh water, too fresh, and what happens? Not only you have a large mismatch between the core water saturation points. We are assuming, of course, that the water saturation points, the lab measurements are accurate and representative. They perceive correctly the core. Look at the free water. There is a large gap. There is a large volume of free water. That makes a big difference. So you have to be very careful. You have to check that not only you have a good match between the core water saturation points, they are reliable to the log curve estimated water saturation. Not only that, you have to verify that you have reasonable amounts of free water. That is the difference between the irreducible water saturation to your water saturation curve final estimated. So this light blue region is the free water saturation, and these are the bulk volumes. So this deep blue is free water, green is oil. Compare this blue band with this one. So that's everything about how to estimate SW using core data. So basically you move water saturation until you have a reasonable match between the core water saturation points and your SWU curves. So we have discussed in this video so far how can we estimate the water salinity from ionic water analysis. We already also saw how to estimate water salinity from core water saturation compared to log water saturation. Now we are going to see how can we compute RWU directly from water bodies and pockets. RWU from water bodies and pockets we're going to study right now needs only logs. The one that we just saw before, core water saturation versus water saturation curve from log, requires blocks and core. The first thing we have to do is to identify water bodies and pockets. So what is a water body? Water body in a reservoir is simply a zone that is full of water. So we don't have oil or we don't have gas. It's a full zone with water. And the theory to do that, you can get some help from this Geoloid webpage. Basically, it's what is called the Hingle equation. But we have in Geoloid a modification where we go further than that. Basically, it's apparent water saturation, but we use a modification to study that with some amounts of shale. So we still need to apply the equation on clean rocks, rock with low shale. But the original equation from Hingle, as well as the Pickett plot, requires that you should have a completely clean B shell equals 0 rock. Not in this case, so we modify it slightly the equation, so we get with this equation the apparent water saturation by the Indonesia equation to take into account a correction for B shell. This is the equation, so we can see how to compute the apparent water resistivity in partially clean rocks with some amount of shell. So this is an equation that allows some shell amount in the rock. That is important because seldom you can have a completely pure clean rock or clean sand. And those are the ideal equation where the Hingle equation works and the Pickett plot works. So we are going to use this. Basically, you have to identify water bodies. One aquifer, of course, is a water body. You see a large drop in resistivity, that is an aquifer. Here you can apply the Hingle method or this method of estimating RW from water pockets. So this is a water body from here to there. And this is a particularly interesting case of an inner water pocket. That means we have isolated packages, we have isolated pockets, we have a zone that is 100% of water basically that is sealed. So here we have towards the top, we have here a seal, and here we have to the base a seal, and we have below a base zone. So there's no doubt, we have water on the top and oil below. And these are sealed, these are shell. You see that because of the behavior of the gamma ray, high gamma ray, we estimate the B shell from gamma ray, and also we can estimate the B shell from the difference between neutron porosity and density porosity. This is this pink filling and pink curve. Also, if you see in the pore space track the difference between neutron porosity and density porosity, that difference is related to the presence of clays. That is because the neutron porosity is sensible to the amount of hydrogen of the clays. If you see the chemical equation of the clays, they have hydrogen, so that's why. Likewise, if you see some other matrix like quartz or calcite or dolomite, they do not have hydrogen. That is why the neutron porosity curve basically measures or is related to the amount of hydrogen minus the regular density porosity sees or is related to the presence of clays. You see this filling, this yellow filling, that is the difference from the neutron porosity. It's related to shell. So this is shell, this is shell. In this region, what happens? In this region we have a clean rock, not so clean. So you hit here, you see the gamma ray is 50 something. On average maybe around 50, something like that. So we have gamma ray around 50, so it is not very quite clean. So that is why we're using the correction for shell in apparent water resistivity. This is the B shell term. So this is important. Otherwise you won't have a very accurate estimation. So you have to identify water bodies that are reasonably clean, like these ones, and also you expect or you know in advance or suspect that they have water only. no hydrocarbons. You explore the resistivity curve, resistivity track, and here the drip resistivity, and here more or less you see, well, this is a well with very low resistivity. Beyond 5 or 6.0 ohms meters, you can consider basically a threshold for pay and non-pay in this particular well. And you see here the resistivity is smaller. So the resistivity here is around, say, approximately 5.0 or something like that. And the resistivity in this pay zone, let's click here, is around 14. That is a difference related to the presence of oil. Here we have a water pocket. We have a seal here. So you have to highlight this zone and this zone. And inside that, you are going to compute the apparent water resistivity. And from the apparent water resistivity, you compute the salinity. And after you have RW and water salinity, you compute the whole collection of equations, including water saturation. We have to make an indicator flag for the presence of the water pockets. We want a 1.0 flag here and 1.0 flag here, or 0 or -1 elsewhere. So you go to upscaling and filterings. We already did that. Water pocket flags. You go to zonation. You want to detect water pockets. There is a flag, and you have to filter by the stratigraphy unit, that is H2O. You have to put that in slashes. Let me show the stratigraphy. These are the water pockets for different well. So we have a top and base, and the name of the zone is H2O. So in the stratigraphy, the upscaling and filtering is looking for H2O. This one is looking here, and makes an indicator flag. Then you go to compute apparent water resistivity, but not any apparent water resistivity. It should have some correction for shale. One of the best equations for this is RW Indonesia. So we studied that equation, it's on the website. We recommend you to apply that instead to use the regular Archie apparent water resistivity. Unless you have a very clean rock, very clean sandstone or something like that, which seldom occurs. So let's open this one and see how it computes that. Output, resistivity, we put the Indonesia equation. It asks you for all these parameters. More detail, you can find it from the website. Have a look on this. It gives you the apparent water resistivity. And if you have a water body, then the apparent water resistivity gives the same value of the correct RW, the formation water resistivity. Once you identify a water body or a water pocket and with low shale, and if you have high heterogeneity on porosity, even better, then you can compute right away RW. Compute this. And then when you have RW, you go to the next equation, which is salinity. This is the equation. So you have to have the temperature of your reservoir, and you put the former computed RW, which is the apparent water resistivity in a clean body, and that gives you right away the salinity. And this is the salinity. So the blue curve is the salinity curve, and the red one is the salinity average. The red one is this one. This is an average, simply. Intensive upscaling, the curve, 110. And 110 is the salinity already computed as a curve. You apply it everywhere on units. And that's it, to display that. So we have here in this particular case, your best salinity is 11,000. You see the red string there. Best salinity is 11,000. And the salinity curve is around close to 11,000. This is another well for which we have an aquifer as a water body, so you can apply the same techniques for that. This is all for today. Please share this video among your colleagues and enjoy the rest of today. Thank you very much.